Swayam Prabha. Digital India. Educated India.
Welcome back. Let us continue our discussion on turbulent combustion. So, this is where we actually stopped in the previous lecture, that looking at the different sources of combustion related research, where one can find, apart from all the textbook and other things, one may look at these resources to see the ongoing work and the advanced topics and combustion related research. Now, moving ahead, we can look at some of the fundamentals of this combustion process, where we look at first the chemical reaction. So, what happens? This is a sample chemical reaction which is happening, and there are multiple species. This is 1, 2, 3, 4. So, if one look at this particular system, so there are species, 4 number of species which are involved here, and one side you call it reactant and the other side you product. So, here the CO and H2, they are reactant, they react to each other, and finally you get the products in terms of CO2 and H2. So, there are different species. So, when this kind of chemical reaction takes place, so it is a rearrangement of atoms between colliding molecules. So, if you look at both the sides of these particular equations, your atoms are sort of maintained or balanced. So, where the atoms are conserved, at the same time molecules are not conserved. So, you look at this particular one which is containing with hydrogen when it reacts to air. So, this whole thing one can treat as air, where you have oxygen and nitrogen by different percentages, and here you can look at it, the molecules are not conserved. So, there are few things one has to know. The one of the important things is the mole number. So, how do you define these things? Typically 1 mole corresponds to a number which is 6.023 into 10 to the power 23 particles. So, this could be atoms, molecules, or any chemical species. See, this particular number is known as Avogadro's constant. So, every one molecule of the species, now one can define the important thing is the mole fraction, which will terminate like xi, and I where stands for that particular species. So, the mole fraction of ith species is represented as xi, and it will be defined as xi equals to Ni divided by summation of 1 to s n j. Now, Ni here is the mole number of ith species, and S is total number of species involved in this process. So, what happens if you have S number of species which are involved, then their individual mole number is corresponding to Nj. So, the mole fraction is the particular species mole number with the ratio with the total mole of the all the reacting species they are involved there. So, you can find out the mole fraction in that way. Now, another important definition is the mass fraction, because these are some of the fundamental definition one would require while we move along with the other definition. So, this is again ith species mass fraction. How we define it? It is individual species mass divided by j equals to 1 to s mj. So, it is a particular mass of that species ith species divided by the total mass of the system. So, that is how you define the mass fraction. Now, one can define the molar mass or Mi, which would be basically the molar mass is, for example, if you have CH4, the molar mass of CH4 is 16 gram per mole. Similarly, molar mass for hydrogen is 2 gram per mole. Molar mass of, for example, O2 is 32 gram per mole. Okay. So, the molar mass for a particular species is represented as Mi. So, one should not get confused with the molecular weight here with the molar mass. Okay. So, that would get you the definition of this molar mass and all these things. Now, one can find out one more thing is the mean molar mass, which is mean molar mass, that is m bar. So, this should be the mixture of species which are involved in that particular system and you get the total. So, mean molar mass will be summation of xi to mi, that means individual species molar mass multiplied with its individual molar mass to the mole fraction will get you the mean molar mass. So, where always S is the number of species which are involved in the system. So, one can correlate this mole fraction, mass fraction nicely. So, one can write Mi to Ni divided by j equals to 1 to s mj nj, that is the mass fraction nicely can be correlated with Mi by xi summation of j 1 to s mj xj, or alternatively xi yi by mi into mean molar mass. So, which can be represented as by j equals to 1 to s yj divided by mj. So, one can find out that thing in that fashion. So, there are some more things which one can define is the one is the density, that is another important things which will come into the picture, which is mass by volume. Then you have molar density, which will be C equals to N by V, that means if you look at the unit kilomole per volume cube or meter cube. So, mean molar mass one can estimate as m by n equals to rho by C. So, now the convention in chemical kinetics is the concentration. So, the concentration C of chemical species are usually shown by the symbol. So, if I say this is the concentration of chemical species, then C for particular species, let us say for example CO2, one can write it would be concentration of CO2 like this. So, this is very common in definition of the kinetics, that usually one defines the concentration of a particular species. For most conditions which are involved in the combustion, it is quite satisfactory to use the perfect gas equation. So, that is one of the equation that one can use is the equation of state or perfect gas equation, where PV would be N R naught T, and if you do the unit balancing, this would be Pascal, this is meter cube, this is mole, this is joule per mole Kelvin, and this is Kelvin, and there are values for R naught is 8.314 joule per mole Kelvin, which is known as universal gas constant. P is essentially your pressure, unit is Pascal, and T is temperature, which is in Kelvin. Now, the thing is that I mean most of the time one uses the ideal equation for gas. This is usually which is used, but when the combustion process encounters high temperature, gas phase temperature, which is near or less. So, high gas phase temperature which is close to almost close to the critical temperature, or pressure are near or above the critical pressure. So, another case could be the pressure and the density or concentration is not then correctly predicted by the ideal gas law. So, there are two conditions where temperature is quite high, which is nearly close to the critical temperature, or pressure is also close to the critical pressure. So, here the ideal gas does not work. So, one has to take the real gas equation, which could be in terms of either van der Waals equation, or there are one Peng Robinson or SRK model. So, there are some of these real gas equation of state which one can use and get the situation. So, depends on the particular process, temperature, pressure and all these things. So, whether the equation of state could be ideal or real, that one has to decide. Now, we can come to some of the basic flame types. So, the basic flame types, so one of the system could be premixed system or premixed flame, that is one of them. Then one can have non-premixed flame. So, we will talk about these flames in details, that is why now we are getting into the classification of different flame types. This could be one of these partially premixed flames. So, these are the three primarily broad categories of flame where you have one premixed, non-premixed, partially premixed. Now, depending on the situation, whether the fluid dynamical behavior is quite nice, in that case the premixed flame can be of two types. One could be laminar, or other ways it could be turbulent. Similarly, this is also a case for other two flames. Non-premixed flame would also could be of two types, depending on the laminar or turbulent, and this case also it could be laminar or turbulent. Now, why we are broadly categorizing these flames into different regime? Because the characteristics of premixed flame is quite different from the non-premixed flame, and at the same time partially premixed flames are different from these two. So, apart from this classification, there could be other some of these flames like triple flames, edge flames. So, these are some of the other information one can actually have regarding the flame classification. Now, if we get to the details of this laminar or turbulent premix flame, what it exactly it is. So, as the name suggests, the premixed, that means your reactants are of two types. One, it will have the fuel. So, that means your fuel and oxidizer. So, they are premixed before they are injected into the combustion chamber. So, that is why the premix comes into the picture, where things are previously before injection they are mixed. So, one can think about the proportion is nice. So, you can have nice combustion and all these details we will see. So, as it suggests, so homogeneously mixed because the combustion event. Now, depending on the fluid behavior, the flow could be laminar or turbulent. So, either you can have laminar premix flame or turbulent premix flame. So, for example, a turbulent premix flame you can have in gasoline engine, then lean premix gas turbine combustion. So, these are the example of your turbulent regime, and this is one of the cross section of your gasoline engines. So, essentially your spark ignition engines which are used in your specifically the engines, either two wheelers or four wheelers, cars, and somewhere the petrol based engine, these are sort of premixed engine. So, this is one of the cross section where you can see the mixture comes through this, and then there is a ignition takes place. So, and then there would be unburned product and burnt product, and then finally there is a movement of the piston. So, that is how you have this combustion process which will get into the different cycles, and the cycles turns out to your forces. Now, another definition is that when you talk about the premix flame is the stoichiometry. So, typically the premix flame is stoichiometric if the flame reactant contains right amount of oxidizer to consume the fuel completely. That means, if I mix x amount of fuel with y amount of oxidizer, so the proportion is rightly mentioned, so that you get in stoichiometric situation. If, for example, the fuel is excess, then one can say it is a fuel rich system. If there is an excess of oxygen, or I would say oxidizer, because it could be burning in oxygen or the fuel could be burned in oxidizer. So, it is a fuel lean system. And typically the standard air composition, as we have seen, this is oxygen and nitrogen, and by volume which it contains. So, we can see an example. For example, let us say we take an hydrocarbon C3H8 and it burns with air, and you get H2O plus CO2 plus the extra amount of nitrogen, because if the nitrogen remain as an inert gas, most of the time nitrogen remain as a inert gas unless or otherwise depending on the temperature where you get the NOx and all these things. So, if you balance out these things, so looking at the system, here you put 5, so this will lead to 4, so this will become then straightway 3, and the rest of the things which will around 18.81 would be nitrogen. Now, one can find out the air fuel stoichiometry is the air fuel ratio. So, it is a mass of air divided by mass of fuel. So, one can calculate this air fuel stoichiometries is, so here the mass of air is 5 into 32. So, this is what one can see through, plus 3.76 into 28 divided by 44. This is the mass of fuel. So, that will get you around 15.6. So, the phi air fuel ratio stoichiometry divided by air fuel ratio actual is called as fuel equivalence ratio. So, this is what, or one can reversely define fuel by air actual to fuel by air stoichiometric. So, that will give you the actual situation where one can find out the equivalence ratio in a premix flame. Now, depending on the phi, for example, phi is 1, obviously it is a stoichiometric condition, stoichiometric combustion. When phi is less than 1, this should be a lean mixture. So, lean mixture lead to lean combustion. At the same time, if phi is greater than 1, it could be rich mixture lead to rich combustion. Now, typically different countries they use some of the different convention. European convention to a certain extent to Japanese also used to air equivalence ratio. So, they call is a air equivalence ratio, which is called is lambda. This is in a nutshell European / Japanese convention. So, that is nothing but 1 by phi. Or certain industries also use excess air ratio, excess oxygen, or similar terminologies are also used. Sometimes the people use excess oxygen, sometimes they use excess air ratio. So, these are the different terminologies which are available and people do use that thing. So, those are which are required for a premix system. Now, what happens when you come down to non-premix system? So, that means clearly as the name suggests, the reactants like your fuel and oxidizer, they are not mixed a priori before the combustion takes place. So, which is the point here, that the fuel and the oxidizer are mixed when they come in contact during the combustion process. That means a priori like your premix combustion, they are not mixed and injected to the combustion chamber. Here they are directly, or to be very specific, they are separately injected to the combustion chamber and they come in contact during the combustion process. So, one of the simple is that example is the candle flame, which we usually burn almost in our daily life, the candle burning. So, that is a typical example of laminar, because the flow is so calm and nice, non-premixed diffusion flame. And there are some examples of your non-premixed turbulent flames, which are hydrogen rocket engine, current aero gas turbines, diesel engines. This is also from your automobile sector. So, these are the examples, some of the examples of your non-premixed system. So, the combustion takes place in the furnace and all these also there comes under non-premixed combustion. So, these are some of the turbulent application of that. This is a typical image of a candle flame where this candle is essentially your solid fuel, this is your carbon, and then obviously from sides you get the oxidizer, that means air. Once you get the air, they keep on burning. But one important things people has to mind it here is that any combustion, whether it is a premix, non-premix, partially premix or a multi-phase, the combustion takes place in gaseous mode only. Even then we are burning candle as a solid, there is a pyrolysis takes place. So, immediately solid transform into gas, and that time scale is so small, and that is why as we have been talking that combustion has a multi-scale problem, because now here first solid to it transform to gas and then the combustion takes place and it happens instantaneously. That is why in a visual normal eye we cannot see that thing happening, rather we see the candle is burning and you get the luminous zone where you get the light, and there would be other reaction zone which you call it C2CH zone. Now, another example if you see, so this is typically happen in a diesel engine combustion which is turbulent in nature, and obviously as you can see that is also quite complex in nature. So, this is turbulent, complex. So, there are different situations to it. You have air inlet, intake port and all these things that comes in, turbulence is there. Then here one more thing is that diesel engine combustion is that here your fuel is in liquid state, that means you have some spray. So, the previous example in the candle flame we have seen the solid burning here. So, solid means solid actually immediately due to the pyrolysis it goes to gaseous state and the burning takes place. Here your liquid has to evaporate. Now, when you have a liquid, this has to again form to gas through evaporation. So, before even evaporation there is a step which goes to atomization, that means the liquid sheet has to break into the smaller droplets and those droplets evaporates and finally you get a gas, and that gas only takes into participation of the combustion process. So, there is a complicated process, and then top of that you have some exhaust is recirculated through easy air, you have heat release, radiation effect, then other complicated stuff like soot and all these things. These are the things which we will see as we go along, but the thing is that as soon as you move from one simple example of candle burning to a diesel engine situation which is a more or less like your realistic situation, the complications actually increases and increases in a different manifold, it increases in a different time scale. One case your solid has to go to gas and then burn, here your liquid has to go through the atomization process. So, this clearly example of your multi-scale multi-physics problem, because liquid has to atomization, then it has to go to basically evaporate and finally forms in forms of a fuel gas, and then the burning takes place and all these things happens. So, it essentially a multi-scale like a problem. So, that gives you an idea about how these turbulent and real life problems actually differs from the simple problems. So, we will stop here and then we will continue the discussion in the next lecture. Thank you.